Hello everyone, my name is Bon Jiang, and today I will present our DBLP data system project. This project works through an end-to-end data engineering and data management workflow, including schema, design, data parsing, SQL analysis, and performance tuning using indexing. And my presentation will cover first, schema design and data acquisition, second, SQL queries and performance analysis, third, indexing strategies and optimization results. DBLP is one of the largest bibliographic datasets in computer science, consisting of millions of XML encoded publication records. These include articles, conference papers, books, editors, authors, and various method views. Because of the raw XML structure is deeply nested and highly irregular, our first task was to design a normalized relational schema that supports efficient analytical queries. So first, for the schema design, our final schema consists of 3 entity tables, publication tables, author tables, editor tables, with 2 relationship tables, author publication and editor publication. This structure retains DBLP's many-to-many relationships while allowing join-based analytical queries. A key design decision was to extract key feature 1 and key feature 2 from the long DBLP key string. These features later allowed us to efficiently group, filter, and identify venues, especially conferences. Next, for data parsing and cleaning, we used a SAX streaming parser to process the extremely large DBLP XML file. This avoided loading the entire dataset into memory. Major cleaning steps included, first, standardizing corrupted year formats, removing whitespace or invalid symbols. Second, removing irrelevant publication tabs such as PhD thesis, master thesis, and www. We then generated 5 CSV files for publication, author publication, editor, and editor publications. These were imported into PostgreSQL SQL using copy followed by constraint creation. Then, for SQL queries and performance analysis, we implemented 8 queries showcasing a variety of SQL capabilities: aggregations, multi-page joins, decade-based grouping, self-joins for co-authors detection, RAGs-based surname extraction, and fuzzy text search. So these queries serve as analytical workloads for evaluating database behavior. Then, for detailed analysis on query running time on half, full, and quarter database, we found that first, query runtime decreases almost linearly with data size. Across most queries, we observed that halving data runtime drops by 50%. Quartering data runtime drops by 65 to 75%. This behavior is typically for analytical workloads dominated by full table scans, large joins, aggregations over many rows. Second, join-heavy queries received dramatic performance gains. Queries with complex operations, especially self-joins and many-to-many expansions, benefit much more from reduced dataset size. The clearest example is Query 7b, which speeds up 40 times. This occurs because Query 7b performs multi-level grouping and filtering over large intermediate join tables. When input size drops, intermediate join results shrink quadratically and leading to disproportionately higher speedups. Third, for the text processing queries show moderate improvement. For query relies on string parsing, surname extraction, like Query 7a. We observed only moderate gains. These queries are CPU bound rather than IO bound, meaning reducing data size helps, but string processing still dominates runtime. Thus, improvements were around 30 to 40%. Fourth, for text search queries didn't scale as dramatically. Queries like unlike text structure showed limited improvements because these operations often require scanning the entire column, even the dataset is reduced. This finding later informed our indexing strategy to accelerate text search efficiently. And for summary, from the runtime table and the scaling analysis, we conclude many queries scale linearly with the dataset size. And join-heavy queries improve superlinearly due to reduced intermediate results. But for text and fuzzy matching queries, have limited scaling due to the CPU-bound operations. And this section of the analysis highlights why indexing is crucial. Without indexes, PostGRE SQL relies heavily on sequential scans, making performance tightly coupled to dataset size. And now, a demonstration video of simple querying on half, full, and quarter datasets, and also the query with indexes will be played. Last but not least, to indexing strategies and performance optimization. So based on the performance observations, we implemented 3 families of indexes. First, the B-tree indexes, used for filters, joins, year-end queries, other lookups. Second, composite indexes, built to accelerate multi-column conditions, and these dramatically helped queries like 7b. Third, GIN indexes, used for accelerating fuzzy text search. These indexes dramatically reduces scan costs and are well suited for DBLP's large text fields. For the indexing results, indexing lead to major performance improvements. For Query 7b, it is 76 times faster. For Query 7a, it improved by 40%. For Query 4, limited improvement due to heavy join logic. These results reinforce a key database principle, that indexes are most effective for selective filtering and text search. They provide less benefit when the bottleneck is complex joins. Then for conclusion, through this project, we completed a full-scale data system pipeline, passed the massive XML using streaming techniques, cleaned and standardized messy real-world data, designed a normalized relational scheme, implemented advanced SQL analytical queries, evaluated performance across multiple dataset skills, and also applied indexing techniques to optimize runtime. The project demonstrates how databases behave under real analytic workloads and how indexing strategies transform query performance. And that's all for my presentation, and thank you for listening.